Hello, I am Pradubati and this is a lecture on decision trees. Here are the outline and the topics we will cover in this lecture. We will discuss the basics of decision trees, how we represent decision trees graphically and mathematically, the process of constructing trees such as data splitting, and common impurity measures and quantitative metrics. Dealing with another topic we'll cover is dealing with and safeguarding against overfitting issues. Although this is not unique to decision trees, it's important. Decision trees, particularly, are very sensitive to overfitting issues. And we will summarize some of the pros and cons of using decision trees, both in classification and regression problems. So, decision tree is a non-parametric supervised learning algorithm. When we say non-parametric in this context, we mean that we make less assumption in the underlying form or in the underlying model. If you remember from our linear regression discussion, one of the important assumptions is there is a linear relationship between the explanatory variables and the target variable. And we also made an assumption that the errors are normally distributed, as Gaussian distributed, right? So we don't make such kind of strong assumption in decision trees. Not only is decision tree a modern machine learning type of predictive modeling approach, we make less theoretical assumptions that may not hold in reality. Okay. Again, supervised means there is training data with annotated labels. That's what supervised learning means. So decision tree is a type of supervised learning as well. So non-parametric means there is no underlying model like Gaussian distribution. In terms of representation, the model graphically is represented as a tree, which I will go over in the next slide. Decision tree typical application are for predicting a target variable, could be quantitative, like numerical values, or qualitative, non-numerical or discrete outcomes. So it can be used both for classification and regression problems. One advantage of decision tree is that you can actually extract decision rules from the tree, which makes it easy to communicate the result of the model to decision makers and non-technical people. So that is, and then we will get into this when we discuss pros and cons. This is one of the advantages of simple decision trees, that you can actually extract rules from it. Something like the if-then statements. Okay, let's discuss about graphical representation now. In graphical form, decision trees are represented as an inverted tree, where you have the root node at the top and the leaf nodes where the actual decisions are made at the bottom. Okay, so part of constructing the tree involves picking a root node, and you split the data set or the observation using the variable that you selected at the root node. Here on the left side, when you get at the leaf node, you have reached at the prediction of the outcome, what category it is for a classification problem. So we will get we will discuss about the details of how, what the proportion of the observation in here, what the majority class is. But in general, when you arrive at a leaf node, the outcome is determined. In subsequent slides, we will discuss about some of the criteria by which you start growing the tree as well as what is involved in selecting a variable for splitting, and also picking or determining a threshold value for the split on that variable. On the right here, you make another, so here on the left, there was, the partitioning was done here, and then we arrived on the left node. Here, we do another partitioning before arriving at a leaf node. These are splitting nodes, so that's the root node here and this node, the blue node right here. These are split nodes because we need to make a decision on further partitioning of the data set. So this is a simple graphical tree representation, and we will discuss as to how we select the splitting variables and the corresponding threshold value on which the splitting is done. And now let's discuss about mathematical representation. How do we represent decision tree mathematically? Here is a formula to calculate the prediction accuracy or the proportion of each region corresponding to this graph right here. Okay, so it's a lot easier to navigate through this formula using regions of a partition graph shown here. So each region here corresponds to a leaf node of the graphical tree we discussed earlier. So let's apply this formula to calculate proportion of observation that fall in one region. Let's take region 1 here. Region 1. This involves two input variables, as you can see, x1 and x2, for determining the outcome of any observation. So let's say in this region we have 10 observations and the outcome variable is a binary. Let's say a yes or no outcome variable. So for each observation in your data set, we'll calculate the indicator function here. This is an indicator function. An indicator function is nothing but the mapping of an input into a binary output. So the indicator becomes 1 if the outcome of the observation belongs to one of the class of interest and 0 otherwise. So that's what indicator function is. So for a binary case, the indicator function for each variable returns the outcome based on whether that observation belongs to the class of interest or not, and we sum over all of the observation. So in this case, we have 10 observations in this region, in region 1, and if 8 of the observations belong to the class of interest, the sum becomes 8 here, and we normalize by the total, which is 10, and that gives us a proportion of 0.8. So what it means is 80% of the observations is from the class of interest. This expression on the sum indicates that the x value should be in that region for applying the indicator function. So again, in this case, the point estimate of the proportion is 0.8 or 80%. Of course, there is uncertainty, which means in future prediction, if an observation falls in this region, region 1, we estimate it to be of the class of interest with a 0.8 accuracy. So and that was for a classification problem. So there is an uncertainty in that sense. So this classification problem, but the logic works for the most part for regression application as well, except that instead of counting the number of observations as we just did from the given class, we will be taking the average of the outcome variable since it's a numerical output for determining what will be the value of the outcome. So you take the average and that becomes the prediction. Okay, now let's discuss about how we do the construction of the tree. In general, we apply two steps, one for the initial construction and another one called pruning, which involves trimming the tree and removing complexity. I'm not going to spend a lot of time here discussing about the pruning step because I have some dedicated slides about how pruning is done, except to say that there are two types of pruning, pre-pruning and post-pruning. In pre-pruning, the pruning is done as part of the fitting the tree, while in post-pruning, the pruning is done after the tree is fully grown, but we will discuss later. So the initial construction involves selecting variables, and optimal value is called the threshold for splitting on that selected variables. So you have a set of explanatory variables, input variables, and at every iteration or step of constructing the tree, you need to select the variable that optimizes a given criteria, which we will discuss in a bit, and then pick a threshold value for it. For a continuous variable, you pick a threshold value for the splitting, okay? For a categorical variable, you pick a class that optimizes the criteria. Both involve some kind of criteria, but in a different approach. So in most of the cases, even the continuous variable is converted to a categorical variable for the purpose of splitting decision. So you recursively split the data by selecting a variable and a threshold value for it. And when you arrive at a node where every observation falls into one class, then that is a perfect prediction and you stop the splitting there, which means you have identified a leaf node for making the prediction. But typically we don't keep splitting until all observations fall in a node, because that will cause overfitting issues, and then which we'll discuss later as well. So the algorithm, the recursive partitioning that I just discussed is a type of divide and conquer approach, in the sense that at every node selection step, we make data splitting that is, we partition the data into subsets, and we make the decision based on that subset. Okay, so the goal of splitting the data set or partitioning the observation is to increase the homogeneity of the observations. It means using some kind of criteria that I'll discuss in a bit. We measure the impurity of the node, okay, and the partitioning continues until one of the following conditions are satisfied. First, the first one is you no longer have any more variables to do the splitting on, which means you used all the variables. So there is no variables that help you making further partitioning. Second, you don't have any more observation, which means all the observation fell in one of the nodes that's already in the tree. And third, any further partitioning is not increasing the homogeneity or it's not decreasing the impurity of the node. So if one of these happens, then you stop splitting the observation or growing the tree. So that is how the partitioning logic works. And the decision of selecting a variable and determining a splitting point that we call threshold is a type of greedy search. It is greedy search in the sense that we make the decision with the information available at that iteration, at that step. And that means the decision is made locally and it may not be optimal globally. That is to say that in the next step or in the next iteration of fitting the decision tree, if we learn that the earlier decision was not optimal, given what we know now in the current iteration, we don't revisit the earlier decision. We just move on. So it is greedy in the sense that each decision is locally optimal, but may not be globally optimal. In terms of fitting or growing decision trees, there are different algorithms, but the two common ones that we will discuss here are information gain based and GNI index based. Information gain, it came from computer science domain, like ID3, C45. Those are the kind of algorithm that implement information gain. And GNI index was first introduced by the CART algorithm. There's also a very simplistic metric which only involves counting the classification error. So this is not a formal criteria, you just count, but in general is not widely used. Okay, so let's focus on the two criteria for information gain in GNI index. An important consideration about selecting a variable and determining a splitting point is that they are a function of the type of variable we deal with. In a typical model fitting activity, you have a combination of continuous and categorical input variables. In this lecture, we mainly focus on classification application of a decision tree where the outcome is a categorical variable. But you can have categorical or continuous variables or some combination of the two, and the selection criteria is dictated partly by the type of the variable that you deal with. For nominal variables, you can employ binary or multi-way split. In binary, we split into two using optimal partitioning. I haven't yet formally defined what optimal means, which involves some quantitative metric that we're going to discuss. In a multi-way split, we partition into as many splits as the number of categories in that variable, and we make the split based on that. For continuous variable, on the other hand, the binary split considers all possible splits and finds the best cut. But it is computationally expensive as it involves creating histograms, and there's quite involved with checks that you need to perform. So the more feasible approach involves discretization to ordinal categories, which means order categories like low, medium, high. So even for continuous variables, it is done through discretization. Now let's discuss some of the criteria about which we make optimal decision that I mentioned a minute ago. Information gain uses entropy, which is a measure of uncertainty. That is, it measures how much uncertainty we have in a given variable. Okay. In the context of data partitioning decision at each node, the entropy is 0 when we have a pure set. Basically, one class has all the observations, and there is no uncertainty in that case, so the entropy is 0. For instance, if we split it into two, that's a binary split, and if all the observations go into one of the subsets, that subset will not have any uncertainty, and the entropy will be the smallest, or 0, which represents no uncertainty. If we have relatively the same number of observations from both classes, then you have the maximum disorder, and the entropy is the maximum, which is 1. Mathematically, here is the formula to calculate entropy. We sum over the product of the relative frequency of the case class and its log. And you take the negative of that to correct for the fact that the log of a fraction is negative. Typically, we use base 2 for the log, but this is how you calculate entropy. Okay, then how do we actually use the information gain to optimally select the variable that increases the homogeneity or decreases the impurity of the node. Here for a binary case, to split the data D into D1 and D2 partitions, we first calculate the entropy using the formula we just discussed on the entire data set before the split. So you have all the observation, you calculate the entropy before the split. Then we make our split and calculate the entropy again, like for here, like the sum of the two entropies for the two subsets. So you have partition 1 and partition 2, you calculate the entropy for each one of them. This term right here these are weights. The proportion of the observation from each class are used as weights. How, to the extent that class, the entropy of that class influences the overall entropy is, so these are basically weights for each one based on their frequency. So we calculate the entropy for the two and we add them together. And we take the difference of the entropy before the split was done and the entropy after the split. Okay, we take the difference between the two. The result is the information, the information gain, which is the amount of uncertainty reduced by the split. And we do this for every variable, and we take the variable with the highest information gain. Once we go through this formula for every variable, we pick the one that provides the largest gain or the biggest reduction in the uncertainty of the variable. So that is how we pick the right variable, the optimal variable. As we discussed, another metric we use is GNI index, as used by the Carth algorithm. For the most part, the two produce same result. Mathematically as well, they use similar formulation. Just we replace the log of the proportion with the complement of the proportion. But the formulation is similar. Let's try to explain this using a graph here. It's a bit easier. We have entropy as red and GNI index as blue line. We also have that misclassification error that I mentioned earlier, which is a black line, but it is rarely used in real-world applications, so we're not going to spend much time on that one. So the horizontal axis is the proportion of observation from one of the classes. Here the application is for a binary case, so we have only two classes. When we have the same number of observation from both classes, we have the most uncertainty and the entropy is a maximum. So here, a condition where you have relatively the same number of observations from each class, that means there's a lot of uncertainty. And entropy, GNI index, all of them are the max, just the actual values are different. Entropy is 1 here, and here the value for a GNI index. Both are the max at that scenario. But as you go to the left or right, the number of observation from one class decreases and increases from the other class. And at the extreme end of both, we have observation from only one of the classes, and both the entropy and the GNI index are the minimum. At the extreme end, both are the minimum, which is 0. So at the extreme values of the proportions, there is no uncertainty because you have one observation from one set to a set. There is no uncertainty in there. So that's how we measure the impurity of the node. The objective of the splitting is to minimize the impurity. So you try to maximize impurity. To minimize impurity, which means more observation from the same class. That's the target. And then these two criteria allow you to be able to do that. Let's review some of the things we discussed so far using a simple example application. So This is a weather data, and I'm not gonna going to focus on the code. So I did this using R, not Python. And the outcome variable is about whether or not it will rain tomorrow. That's a prediction. So the binary outcome on whether on rain for the next day. As you can see, the distribution in the sample data here is 84% of the cases indicate rain, and the remaining 16% not rain. So even without a model, if you just predict based on that distribution of no rain, you will be correct 84% of the time. So a model has to do a bit better than that. So how does the tree construction work here? Okay. By the way, the text you see here at the top is a bunch of if-then-like statements of the same model, while the graph is a tree representation of the model. Now, different algorithms give a little different perspective, but effectively the same thing. So the first thing we do is determining the root node. To do that, as we discussed earlier, we calculate the information gain depending on the algorithm you use. It could be Genoa index or information gain. This particular one is for R-part implementation in R, which is a type of recursive partitioning and regression tree algorithm. And your approach is based on a conditional tree, which also does a statistical test for the splitting. And that means it does the splitting only if the reduction in the uncertainty is statistically significant. So the root node here is pressure 3 ppm. So that is the variable that was selected based on the criteria, and the split threshold is 1012 for this variable. So that is where we split the observations, and every observation less than 1012 in pressure 3 ppm variable go to the left, and the others to the right branch of the tree. Okay, so we made our first partitioning of the data based on this condition. Now the distribution now changed from 84:16 to 92:8 on the left, and on the right to 50 versus 48 for the two classes. So here the uncertainty went down on the left branch. Okay, remember it is a recursive algorithm, so we do the checks again, and here we pick the optimal variable to be clock 3 ppm, and the corresponding threshold is 7.5. Okay, and then we do further splitting at this point, and it will give us further reduction of uncertainty. Go the distribution, change it to 95 versus 5 now. Okay, and at this point, the criteria indicates there is no further reduction of uncertainty, and we stop and we arrived at the leaf node, and then this is where we make the prediction. You see the small percentage numbers you see here, the proportion of the observation in the training sample that fell in this region. We did the same thing on the right. We follow the same approach. The next variable was sunshine, along with 8.9 for threshold, and the observations less than 8.9 go to the left and indicate the no category, no rain category, and the ones on the right represent the yes. So this is how simple binary classification works. Okay, now let's move on and discuss about overfitting issue. It's not a unique thing to decision tree, but we will discuss overfitting from the perspective of decision tree. And it is a common problem in decision tree, especially when they become too complex. It occurs when the model learns the training data too well, to the point where it starts to memorize the noise and outliers in the data. And that can lead to poor performance on new, unseen future data. during the actual use of the model. Now, some key indications or signs of overfitting in the decision tree include excessive branching. So if a tree with many branches and leaves, then that's some indication of overfitting. Also, if you experience poor performance on the validation set, you remember in supervised learning, you do the training and then you do validation on the separate independent test set. So while the model may perform well on the training set, its performance on a separate validation set may be significantly worse. Another one is high variance. That means the model has high sensitivity to small changes in the training data. So if you see that, that's an indication of overfit. So what effectively means, if you from the same domain, if you just take another sample, which is supposed to be from the same with the same distribution and the same characteristics, and if fit another model on that new sample, and then you see a drastically different model, so that is some indication of overfitting. Some cause of overfitting in decision tree, excessive depth. If the trees are allowed to grow too deep, you can easily fit the noise and the data. Lack of pruning. Pruning is an important thing that we looked at to deal with overfitting issues. So pruning means just removing unnecessary branches from the tree to simplify it and to make it generalize well. And also, if you have a lot of imbalance in the data, that is, if one of the classes, let's say in the binary case, dominate the other, then it is heavily skewed towards one of the classes, and the tree may become biased toward that class, and that may be indication of overfitting. Some common techniques to deal with overfitting issues is, like I said, pruning, and try to restrict the depth of the tree. And also you can earlier make feature selection and optimally select features that are appropriate. And cross-validation. So this is a different type of evaluating the models on the same training. Just a little bit different from the way separate independent test is used. Cross-validation is just a different way of we will discuss that when we learn about other classification algorithms, but cross-validation is another way to deal with it. So by carefully considering these factors and implementing appropriate techniques, you can effectively prevent overfitting in your decision tree and build models that generalize well. It's very, very important in machine learning in general to safeguard against overfitting. Here is the same thing, overfitting using a graph. So this one is using error, misclassification error. This is the horizontal is a number of nodes in the tree. So this is an indication of how complex your model is. So and then the red line is that performance, the misclassification error on the training set, and the blue line here is on the separate test set. So as the model gets more complex with increased number of nodes as you go there, and then unrealistically the training set error goes down. So as it becomes more complex and fit all the noise in the data, the training set performance still shows improvement. But as you can see here in the blue line, at some point here, close to 50 number of nodes, then its performance decreases on the independent test. So although the training error goes down on the training, it's an entirely different story using the independent test. So this is where part of the fitting, you monitor this performance here in terms of misclassification error, and then you stop growing the tree further when you see performance degradation on the test set. Okay, so that's just a different representation of the same issue that we discussed in the earlier slide. I kind of already discussed this in the previous slides about how you mitigate overfitting. So this is particularly using pre-pruning. It is a technique used in decision tree to prevent overfitting by stopping the tree's growth before it becomes too complex. So it involves setting predetermined criteria to limit the tree depth or size. Some key aspects of pre-pruning is early termination. Okay, the tree growth is stopped when a specific condition is met. The condition could be maximum depth, a minimum number of samples per leaf, or maximum number of leaves. So any of the criteria you use that to do the early termination. It is simplicity. It has simplicity. Pre-pruning, it's generally simpler to implement than post-pruning that we're going to discuss in the next slide, as it doesn't require building the full tree first, right? You do the pruning as part of the build. You don't have to wait until the tree is fully grown. And there are some advantages. It's efficient. It is efficient because it just, especially if you consider for a large data set, because you don't have to build the full tree, it's more efficient. And again, it's simplistic. The process is straightforward and easier to understand. Some disadvantages of that is it's prone to underfitting. Remember, we talked about overfitting. Underfitting is a model has not trained enough. It doesn't have sufficient knowledge about your data set. Compared to post-pruning, it is, I think it's a simpler approach, and although post-pruning gives better results, we'll discuss about post-pruning in the next one. But in general, pre-pruning is a useful technique for limiting the complexity of your decision tree and prevent, or at least mitigate overfitting. So always remember that it's important to balance the benefits of simplicity with potential underfitting and overfitting issues. The other one is post-pruning, the other way to mitigate overfitting. And post-pruning is a technique used in decision trees to prevent overfitting by removing unnecessary branches from a fully grown tree after it has been already constructed. And this approach allows the tree to learn the data more thoroughly before being pruned, often leading to better performance. Some key things about post-pruning. It is full tree construction, that the fact that the decision tree is grown to its maximum depth without any restriction. And the branches are systematically removed based on the pruning criteria, typically using the validation set. So you apply the criteria on a validation set. And you also leverage performance evaluation. So the pruned tree performance is evaluated on the validation set to determine if it improves over the unpruned tree. Some common techniques in post-pruning is there are cost complexity pruning method, there are error-based pruning methods, and there are others as well. The advantage of post-pruning is flexible. It allows the tree to learn the data more thoroughly before being pruned. And it's adaptable. The pruning criteria can be adjusted based on the performance of the validation set. You see the performance on the validation set, and then you can adjust the pruning. So, but similar to the pre-pruning, it reduces the risk of overfitting. And also, it's not, remember when we talked about pre-pruning, it tends to underfit. That is not an issue here. It does have some disadvantages. Unlike the pre-pruning, it is it is computationally expensive because it is done after the tree has fully grown. And also it is prone to overfitting, although it is a way to mitigate it. It's not as good as the pre-pruning in terms of that, especially if the pruning criteria is not carefully chosen, then the prune tree may still be overfit. So in summary, it's another way of mitigating overfitting issues by fully growing the tree and then do the pruning. Now let's discuss some pros and cons of decision trees. So one of the pros is it is interpretability. Decision trees are easier to visualize and understand, and that makes them good choice for tasks where model explainability is important. Earlier we discussed about non-parametric. That means they don't require assumption about the underlying data distribution, so that is an advantage. They can handle both categorical and numerical data as well. So if most real-world data sets have some combination of those kind of variables, so you can easily apply decision tree for that. And also you can have the algorithm can provide information about the importance of the different variables or features in the model. So you can actually rank the importance of variables. So that goes with the explainability advantage. They tend to be robust to outliers. Decision trees are relatively robust to outlier observation. Some disadvantage and cons. Overfitting is the one that we discussed a lot. They are prone to overfitting, especially when they become too complex. That means poor performance on future unseen data. Instability is another issue. That means small changes in the training data can lead to significant changes in the structure of the tree. So that means they become less stable. They're biased toward majority class. So if you have a lot of imbalance, then they are biased toward the majority class. Now, this is the missing value case. They do handle, while decision trees can handle missing values, they may not do so optimally, especially for large data sets. If you have large data sets with a large number of missing data, although decision tree can work with missing values, for that kind of scenario, they may not work optimally. So now, to mitigate these drawbacks, decision trees are often used in ensemble way. We're not gonna learn about that here. You will cover that in subsequent courses in the program, like random forest, gradient boosting. These are ways to combine multiple simple decision trees to improve performance and reduce overfitting issues. As I mentioned, ensemble trees are a class of machine learning algorithms that combine multiple decision trees, in some cases thousands of them, to make more powerful predictions. And by combining the prediction of individual trees, this method can achieve better performance than a single tree alone. Now, common ensemble, there are variations of these. But common ensemble algorithms include boosting, bagging, and random forest. But as I said, we are not going to study ensemble or more advanced forms of decision trees. Those will be covered in future courses. And that will do for decision tree lecture, and thanks for listening.